All right, ECGR 4101, 5101. Welcome. Today's lecture number 12. We're going to start talking about serial. This would be serial communications, not having anything to do with breakfast cereal or anything else like that. So, as always, I start today's discussion with the embedded app of the day. And I've got a choice of two. I think I'm going to do this one. Today's app of the day is going to be the parallax ping sensor. And the first thought, or the first question I have from somebody is going to be, what is that?
What the heck is that?
What the heck is that? That's a good thing. And the other thing is, it's a sensor. How could it be an embedded app, right? Go ahead.
It needs a microcontroller to actually tell the distance.
It needs a microcontroller from where to tell the distance. Okay, let's take a look at what we have. We have a beautiful interface here. What does this say? Ground, 5 volts, signal. That's pretty easy, right? So it's obvious that there's 3 specific interface pins, ground and 5 volt. That's pretty darn understandable, right? What do you think SIG is? Signal. You know, you are.
The ping input.
Say that again?
The ping input, I assume that's used for game shows and stuff. And then when a person presses a button, that's where the input comes in.
Okay, that's interesting. Game show. Ping. What does the word ping mean?
Or something like that.
Say that again?
It's like a timer, sort of, to see how long it takes.
Okay, time to see how long. Does anybody know the origin of the word ping? Sonar, submarines. So in the old days, a submarine underwater would send out a audible ping underwater to try and sense the distance between it and something else, because the something else would reflect back some of the energy of the signal. Why was that used? Well, back in the old days, probably 40s or so, World War II, you would set your torpedoes for a certain distance because you wouldn't want to fire a torpedo at a ship and have it go off too early as it was hitting junk or maybe hitting the waves as it's going along the surface towards the target. And you didn't want it to fire off too far away. You wanted to actually arm the explosive a couple 100 feet in front of the actual ship that you were shooting at. And so they would ping, find the distance, set your fuse or set your device on the torpedo to say, all right, activate the triggering mechanism that when it hits the side of the hull, it explodes, because you want to do that a few 100 feet in front of it. Well, there's one problem with that in World War II. Anytime you did an audible ping, guess what else you did? You gave yourself away. You kind of told somebody, I just heard a ping over that way. There's probably a device over that way. So, ping sounds like it's sound, right? Same thing above ground, and this is a sensor that will do that. It sends out an audible ping somewhere between 30 and 40 kilohertz, and it's going to get back from that audible ping a distance. Now, it's a pretty low frequency. Can you hear that? What's your audible frequency that you can hear? Say it again?
20 hertz to 20 kilohertz.
Okay, 20 hertz to
20 kilohertz.
20 kilohertz. Well, that's for people like you, right? For older people like me, it actually goes down some every 10 years or so that one's alive. Are you familiar with the mosquito device?
Yeah.
Have you ever heard of that?
Yeah.
In fact, that's an interesting... I got enough time to waste today. Let's go ahead and do that. I'm going to... I like it. Awesome. Distracted. Well, I mean, as it is, it's nice to actually look at some examples of embedded systems to see what the objective of some of this stuff. Ask me later. Yay. All right. Gumby.
Yeah.
What is this? Is it Gumby's?
Click it.
90th birthday.
Click it. Click the balls.
Oh.
There's more.
Oh, is this Pokey?
No, Pokey's the orange one.
Oh, look at that. How exciting. Oh, you guys are just too much. All right, now that we've looked at this, it takes so little to amuse me, right? Oh, look. Teen deterrent device. So the whole idea is that mosquito was invented to keep you meddling kids away from businesses that were doing business. Yeah. In other words, it works on the whole aspect that your hearing is much better when you're between 13 and 25, and then as you get older, you just can't hear as well. So if you think that's funny, we'll go down here. So according to this, I should be able to hear, by the way, this stuff will make dogs howl, all right? Let's see if you can hear this. Well, anybody should be able to hear this. Yeah, can you hear that?
Yeah.
All right, so I heard that. So that means I must be younger than 60. Let's see, can I hear this one? I can barely hear this. I won't do it too long. All right, should I be able to hear this one? I can't hear this one. Can you guys hear it? Yeah. How about this one? By the way, who's older than 25 in here? Is it one? You're not 25? Oh, okay. One? All right, you're my test case, right? All right, can you hear this?
Funny enough.
How many of you actually heard that one?
Do it again.
Yeah.
Keep it louder.
Actually, yeah. Come on, where's my...
Yeah, I didn't hear that.
I'm 24, but I still like to think
Can you guys hear that?
Yeah.
I can hear it start off. I can hear it.
He started talking.
All right, here we go. You ready? This is going to blow some of you. I'm going to lower this down.
I can hear that.
Ahmad, may I ask how old you are? 24. All right. So keep in mind that one sound range is different. So okay, so we got distracted. All right. So there's a device out there, by the way, that will fire off depending on who you want to drive off, an 18 kilohertz or 17 kilohertz, and actually it's adjustable by who you want to drive away.
So we can drive off old people.
You could drive off, if you want to, you could drive off old people. Here's the thing that I love. They even have a product. This is the ultimate in product. Where'd it go?
Why would people want to do that?
I know, right? I was just thinking about it.
I mean,
Hey, you can do just teenagers? And some sort of
Music mosquito. I love this. This is the ultimate in music mosquito. It is playing classical music outside will also deter young people from wanting to stay there. Yeah, if you basically play old fogey music, it'll keep you away. But think about this. This is an embedded system as well, right? Because you're in that case, you're sending out with a speaker. You're actually using microprocessor control because you're switching which frequency you're sending out. You are actually driving away somebody on some audible frequency. And actually, somebody mentioned you can have a ringtone that has that.
Mm-hmm.
Somebody mentioned that you can get a ringtone for your phone, which kind of spoofs the old fogies like instructors like me from knowing if it's ringing. But that would drive me nuts. And it will make the dogs howl. Anyhow, this is not good. Ooh, that's because they hit the wrong button. I said VCR. All right, so here we go. So this is sonar. Notice there's two. How do you think that is? All right, send and receive. So there's some of them actually have the same package, the audible type, or the same CAN package that is both the transmitter and receiver. Here's why it's an embedded system. And I'm going to peel off this little sticker on the back that says quality. I've got to put on my glasses to be able to see this. QC passed. Because I want to see what's under here. I grabbed the wrong one. Oh well. Wow. There's a lot of stuff on the back here. So much stuff. Let's take a look at this. There is, oh man, there's still goo on this. All right, it says parallax. What does parallax make? Garbage. Okay, they make chips. Chips that have stuff on it. What do we see right here? It says 4.0M.
Oscillator.
That is an oscillator. What does an oscillator do?
Resonates
It generates a clock. All right? There is also here a lot of other chips. In particular, let's see if I can zoom in on this one anymore. No. Wow, I can still go further. NXP, if this thing would stop autofocusing. I can't see what it is too well. But then there's also here some other components associated with all of this. I can assure you, what is this one that says parallax? What will it be? Most likely a processor. So the way that this works is that you give it a signal. So let's zoom out on this again. So the whole idea on this application of the day is that you will give it a signal on the sig line. And the processor itself is going to be doing that. So I should say your processor, your microcontroller. So this is actually from the microcontroller, like your Renaissance board. This goes directly to our microprocessor there. The microprocessor there will automatically handle, hey, I was given the rising edge of a signal. I will send out a pulse, then I will sit back and I will listen. And it actually will record, or it will actually listen for energy. And when it reaches a certain threshold of energy, meaning I got a good reflection back from something else, then it will return a pulse from the ping. And this is the, it is not just called a ping, it's called a ping. Here we go. That's how they spell it. So there's going to be a certain threshold of energy associated with the sound that will reflect back. For example, if I have my ping and I'm shooting up there, right? It's going to have a certain range that it works. It'll work in a range, and they'll show you in the data sheet about this much. And of course, as it works out, that range gets bigger, but then the energy dissipates some. So it's looking for a big bulk of something that will reflect the sound energy back. If it doesn't find it, it'll time out and it'll just basically say, all right, after, I think the range of this is 30 feet, after about the time that 30 feet would occur, it just says, I give up, there's nothing out there. However, if it detects something, again, it'll give you back the square wave. So as I was pointing up there, that's looks like more than 30 feet. I probably would time out. If I were to go a little bit down, I might get that row of people. A little bit down more, I might get this row of people. A little bit down more, I get this row of people. So it comes down to how close the biggest thing is. One problem with that is that if you have the device and you set it on a platform, you got to make sure that the platform's not in the way because it may actually reflect off the platform. But again, when you have a reflection, think about your physics, right? What happens to the energy if I were to point at, I'll give you an example. If I were at this point, so the camera can see it too, and I were to point down at 45 degrees at the floor, where's the sound energy going? That way, right? Eventually some of it might come back. If I go straight, then I have some reflecting off the top, some reflecting off the floor. It'll probably get that chair, probably get that. So if I move further out here, it'll come back if I'm close enough here. So the one problem with any type of reflective type of sensor is that you have to have a nice surface that it's going to rebound off of. All right? Any questions about the ping? That is today's embedded application. So let's start, and we're going to talk about serial communications. Specifically, I need to take a... oh man, look what time it is already. All right, I need to take a survey. How many of you have a good understanding of communications in general? The 7 layers of the protocol of OSI. Yeah, not too many, all right? How many of you have done RS-232 communications and know how it works? Yeah, okay. That was a senior design project, wasn't it? Robotics. Okay. I don't remember. Well, hardly anybody raised their hand. So let's go over communications basics. This is usually what I get, and so to start from scratch is what I typically have to do. And without further ado, we're going to look at serial communications. So, in serial, by the way, these will be made available to you folks online. So in serial communications, we're going to look at some general concepts, and then we're going to look at what is RS-232, UART. I'll talk a little bit about polled and interrupt driven. I don't think I'm going to get the code examples here in this version, but I will a little bit later in my next version, or in the next lecture. And I'm going to talk about stuff in general for this lecture, and then in the next one, I'm going to go into more detail about what it is. So let's look at data communications. Back a long time ago, this is when we wrote on stone tablets and stuff. In the computer world, it was difficult for 2 different manufacturers to communicate with each other with their own equipment. IBM was one of the biggest ones at that time in the 50s and 60s, and they communicated well with anything they had, but they realized that there would be a need to communicate between 2 different entities. So there was a standard established that said, all right, we will identify specifically 7 layers of data communications protocols that will allow us to communicate between 2 different devices. We are mostly worried about layer number 1, the physical layer. And we will kind of look at data link number 2. Everything above that is carried out in a embedded or in a data communications course. And so I'm not going to cover it in this class. But you should know it exists because, for example, applications will use that extensively, and it's good to know that there are some other layers associated with the top ones associated with services for different applications, and then 1 through 4 are usually layers associated with actually transmitting the data intermediately. So you'll typically will see data go through layers 1 through 4, like between one computer here, and it hops to a router, and then it hops to another router, and then hops to another router, and hops to another router. And then when it gets to the end, its end destination, another computer somewhere else, then it will go all the way through layer number 7. Now keep in mind, not all communications have to use all 7 layers. It's just a good way to identify it. And also keep in mind that there are pretty standard types of information that is shared between each layer. And again, I'm not going to go into that. Right? I'm going to dive into physical layer. And in fact, one aspect of the physical layer that I want to talk about is serial communications. Now, the word serial is one at a time, right? As opposed to parallel, many at a time. Typically, when we talk about serial communications, we will use 2 wires. One for transmit, one for receive. There are some devices, like the ping you just saw, didn't that have a very rudimentary form of data communications, right? A single bit, so to speak. A rising edge of a pulse from your microcontroller application to the ping sensor, and then the ping responds with a single pulse. That is a very simple form of serial communications. Same wire. However, we are allowing ourselves to use transmit and receive. And by the way, there are some applications that actually allow you to use different wires or additional wires. Very often, it's very helpful to have a ground that is common between the sending and the receiving device, or I should say, between the 2 devices, because often the 2 devices will send and receive at the same time. Sometimes you need additional information between the 2 devices. There are some protocols available, specifically RS-232, that use things like a clear to send wire and a data terminal ready wire, and just additional wires that say, okay, I'm about to send information, here it comes. It allows you to actually synchronize some of the data. The main thing I want you to realize, of course, is that the receiver from one side has to have a transmitter at the other side. And we're going to be looking at machine 1 and machine 2 for lab number 4. Lab number 4 is going to be posted either today or tomorrow. It's going to be communications between your board and a PC using the RS-232. So, when you're talking about communications, you're talking about sending specific data in an organized way. So the way we organize this in most serial communications is that we worry about sending a byte. Now imagine this. If I want to send a whole bunch of bytes from one machine to another, obviously you're going to have to line up and say, here comes the first one, here comes the second one, here comes the third one, here comes the fourth one, here comes the fifth one, rather than just saying, all right, I've got 64 bytes I'm going to send. Each byte is 8 bits. 8 times 64 is
512.
512. So I'm just going to send 512 bytes or 512 bits at one time. And it sends it out. Why does that not work? What do you think? Okay, so it could get lost. Does that mean it makes a left turn at Albuquerque instead of a right turn at Albuquerque?
No, you don't receive all
By the way, you know who says that, right?
Bugs Bunny.
Bugs Bunny must have made a wrong turn at Albuquerque. All right, so why do you think that is? Why do you not want to send 512 at one time? Can you? That's a good question. Can you?
I guess the receiver is expecting a big chunk.
All right, the receiver is expecting a big chunk. Sounds okay, right?
Except for possible data corruption is a huge package.
Well, data corruption. But you could adjust for that, right? You could just add a couple more bits at the end that gives you some sort of error detection correction, right?
CRC.
That would be a CRC count. Why do you just not send a whole bunch at one time?
Well, correcting that kind of data would take forever.
Ooh, correcting might take forever. That's an option. Or that's
It's hard to sync with so much data in it.
okay, it's hard to what?
Sync.
All right, very hard to sync. All right, imagine two different computers running with two different clocks. This one says it's running at 4 megahertz. This one says it's running at 4 megahertz. Are they really running at 4 megahertz exactly? No, they're off typically by some. One is, plus 1%. The other is minus 1%, right? And so if one is sending so much data at a certain speed, and this one is expecting it at the same speed, but its clock is really a little bit different, eventually the bit that it thinks it's sending over there is just kind of like ignored. Because he's not running fast enough to collect it. And I'll show an example of this in a second. So the reason you send and you kind of asynchronously set your expectations is because you have two different devices running at two different clocks. And how do you do that? Well, you have a start bit. So when one machine is going to send something, it sends a start bit, which lowers its signal from a logic high to a logic low. And at that point, the other receiving device says, okay, I'm about to receive something. I'm going to, because of this edge, I'm able to start receiving it and see what's going on. Because now they said, okay, I received it at the same time. I know that this is the start. Now, with each data bit it sends, why can't it just do that all the time? You think about it, when it's sending each data bit, it's either a 0 or a 1, so you're never assured of having an edge, right? To be able to synchronize it. So what communications people do, designers do, is they send a start bit that says, all right, now start your timing. We agreed at a certain speed, and I'm going to be sending a certain number of bits. By the way, it also pads it at the end with a parity bit. Allows you to check stuff. And then at the end is start bit. So in our message, in this case, we have one start bit. We're sending 8 data bits. That's a nice byte, right? And then a parity bit at the end, which will be used to make a total of number of ones or a number of... the number of ones need to be either odd or even. That's where you've heard the word even or odd parity, right? So the devices that you're communicating between the two have to also agree on a certain speed. Now, if you start having additional machines, you need to actually, and you want to start sending more payload, you want to do more error detection, correction, things like that, then you'll need to add additional data associated with all of these bytes you're sending. If you're sending 1 byte, you can pretty much tell that, yeah, that 1 byte was correct. Or is it? So let's take a look at an example. Let's say that I'm going to send from one place to another, send the byte A0. All right? That's hex. And according to my protocol, I'm going to send the most significant bit first. So I'm going to, from computer 1, I'm going to send, and I'll do the start bit. Now A0 is what in, actually, you know what, I'll send A5. That looks easier. So that's the pattern 1 0 1 0 0 1 0 1. Wasn't that convenient? So then it's going to send logical 0 for the start bit. Then the next bit is going to be logical 1. Then the next bit is going to be logical 0. Then the next bit is going to be logical 1. Then the next bit is going to be logical 0. Then the next bit is going to be logical 1. 0. Sorry. Then the next bit is going to be logical 0. Ignore that glitch. Next one's going to be 1, then 0, then 1. By the way, this is the least significant bit. This is the most significant bit. And then I'm going to have a stop bit. What did I say my stop bit was?
Parity.
Oh, I'll do parity. Let's do a parity bit. And I'll call my parity even. Even parity. Even parity means I make this bit right here either 0 or 1, so that when I add up all the data bits, they equal to... thank you. When I add up all my data bits, they equal to even, if I say it's going to be even parity. So my data bits are 1, 2, 3, 4 ones. So to make sure that I have an even number of bits, including the parity bit, this should be 0. And then I have my stop bit, which is a 1. Stop. That looks horrible. I didn't say stop. Interesting enough, if I immediately then start sending more data, notice I can go down to 0, and that would be my start, right? So I can immediately send another byte. Now, one thing I say is that between my two machines, they have to agree to communicate at the same speed. So, in advance, you have to say you agree on the speed, the number of stop bits, and the parity. And you can have even, odd, or none. You can decide not to have any parity whatsoever. So if this is what I sent, again with comp 1, let's say I have an error. Something happens to the line, right? And I garble some of my bits. So I do my start bit. I do 1, 0, 1. This was start. And then, for some reason, I garble and everything is stuck at 1. And then my stop bit. Also 1. And then I start again. Or then I don't do anything at all. So, oh, I forgot my my parity. And it just so happened that my parity, I'll drop down to 0 at that point in time. You know what? This is a bad example. Let me start all over again. So count 1. Here's my start. And you want to see it? Okay. 1, 0, 1, 0, and then something gets stuck and it's all garbage. 1, 0, 1, 0, 1, 1, 1, 1. And that would be my data. Then comes my even parity. Then comes my stop. All right? So, my computer would look at this that's receiving and it would say, is this okay?
No.
The answer is? Say it louder. It's off by 1. So even though I'm expecting even parity, 1, 2, 3, 4, 5, 6 bits, that means I would expect my even parity bit to be a 0, but it's stuck at 1 because there's some sort of communications fault. So this would be identified as a parity error. And by the way, this is pretty typical. If you have a communications fault, it's usually not a single bit throws here and there. It's usually a whole bunch of stuff. By the way, the other thing pointed out here is that there's no start bit, right? So when this finally goes down, that's when it would first say, oh, here's the next thing that's being communicated. By the way, how long does communications take? Let's look at an example. Let's say, again, we are sending the hex value A5, even parity, 1 stop bit. We're sending at 300 bits per second. How long does this actually take? All right, well, how many bits? The number of bits sent equals 8 data, 1 start, 1 parity, and 1 stop. So 11 bits divided by 300, right? Bits per second. And it equals how much?
Decimal 036 would be
36.6 milliseconds.
You said 0.6?
036.
So 36 milliseconds as somebody said. Well, 36.6, 37 milliseconds. That's a lot of time, isn't it? What's the throughput? How many bytes per second? How many bytes of real data? Well, what does this give you? It gives you a frequency, right? So what's the frequency? 1 over that, which is what? Here, I'll go back up to here, right? One divided by 0.03666666. So the frequency is about 27 bytes per second. That's pretty darn slow. So what I would like you to do is, if I desire to send You got to remind me every so often. Yep. 512 bytes per second. Even parity. One stop bit. What will be my minimum bits per second that I need to communicate at? Go to it.
Five six three two.
Say it again.
5630.
Alright. I'll wait for everybody else. Start bits are always needed. Otherwise, you don't know when you start. All right. Y'all get it? Will you agree that this is what I'm looking at?
Why is it?
You want to send 512 bytes per second, right? By the way, this would be multiplied. And 9 bits?
Wait, why is 9 bits?
10 bits.
What about your parity?
Yeah, you start bit and bit.
11 bits.
Or tell it.
Yeah, just checking.
He was testing us.
I was testing you. Do as I say, not as I do. Yeah. So again, 512 times 11, and as we said, somebody over there, it's 5632 bits per second. Is that one of the standard speeds? Actually, there are, in some of the older microcontrollers, you actually can communicate at just about any speed that you want. But with modern machines, they actually want to synchronize it at certain standard speeds. And I'm going to look to see if I can pull this up. So as it turns out, with our with our bit rate generator, we can communicate at 110, 150, and then nobody's saying, show me that. 150, 300, 600, 1200, 2400, 4800, 9600, 19200. You notice the pattern here? 3125, this is where it gets a little bit funky. And then 38400. I'll go into more detail of this later. These are examples, by the way. So, if I were to have to choose one of the standards, which one would I choose?
192.
Obviously, I want to choose 9600 because I said minimum. So I would send it 9600. By the way, most GPSs, when they're transmitting, are sending at 400 and 4800. Why do you think you communicate so slowly? Any guess? Say that again? Large gap? Okay, large gap, that's one idea. Any other thoughts?
Not a lot of data.
You don't have that much data, and?
Lower bit error rate.
Say that louder.
Lower bit error rate.
Lower bit error rate is typically it as well, and you want to communicate with the lowest common denominator of hardware. Not all the things you're communicating with are PCs that are capable of more than 100 kilohertz or 100 bits. 100 was it 112 kilobits per second? So a lot of devices just cannot communicate that fast. That's why you would choose something a little bit slower. All right. That's a little bit of basics. Let's go on. Oh, I've gone through all these beautiful. All right, so bit error rate versus baud. Actually, the bit error rate is a more appropriate definition of how many data bits are transmitted per second. But there are some situations where you transmit symbols. In other words, you are not transmitting a 0 meaning a 0 and a 1 meaning a 1. Sometimes the communications changes states per second. In other words, you're kind of encoding data. And I'm not going to go into much definition of this. In most cases, though, the bit error rate is equal to the baud rate, meaning you're sending either a 0 or a 1, and you're not encoding it in any special way. By the way, the symbol is represented by a voltage level, so in most situations when you're communicating digitally, it's either 0 or a 1. And a good example of this is with acoustical modems. Remember the old days where you're dialing into something, and it's doing all that noise. It's actually the frequency at which it's sending is associated with the voltage level because you're sending it over analog telephone lines, and so you're able to adjust the voltage. By the way, serial communications are actually identified with something called a space and a mark. As it turns out, a logic 1 is a negative voltage, and a logic 0 is a positive voltage. And the RS-232 communication specification says that you have to have a minimum of plus and minus 3 volts, maximum of plus 25 and minus 25 volts. Most devices nowadays are communicating approximately 5 volts. If you have your typical RS-232 chip. Now keep in mind, what you're going to see is really something like this. You have your processor chip over here, and in this case, let's say we'll connect a little jumper pin. And you have this chip over here called a Maxim 232. And it will take a transmit signal. It will adjust the voltage. That's the name of the company, Maxim, right? You're snickering because it's also the name of a magazine. Sorry.
I just saw Max
32.
And I was like, what Maxim?
Yeah, it's the company's name is Maxim, right? 232 chip, which will adjust this voltage for transmitting out. So this will be a logical 3.3 volts, let's say. And this will convert it based on capacitors and your VCC that you give it to something like 5 volts that's acceptable over here to send out your RS-232 port. You notice the plug on your board, the D shell connector? That's going to be one of the things that you can plug a cable on one side and then plug the other side of the cable into a PC. But you have to make sure your voltage level is going to be appropriate for the PC to read. Now at the other end, the PC is going to have a 232 chip as well, which will then convert its signal that it's receiving into a voltage level that the computer at the other end can actually work with. In this case, your typical PCs will have an internal bus, and it'll work probably somewhere between 3.3 volts and 5 volts at that end. Now, over on this side, we do have your microcontroller. On the board itself, does anybody have a board handy up front? On the board itself is a small chip that actually will do what we call level shift. It will convert the logical 0 to a nice positive voltage that it likes. So if we look carefully at your chip, doesn't show very well. Here is my serial chip. Oh, PCM. Well, that's PCM serial flash. But here's my RS-232 serial. Stop. Serial chip right there, which will allow me to communicate between my my board over here, or my chip over here, and the RS-232 chip to the COM port. Now, what that means is that when you want to communicate, obviously all you have to worry about is logical 0 and logical 1. All you're sending out, and you're telling the serial port, I want to send out this byte. And you know what? The hardware itself is going to take care of the specific signals that you're going to send out. So let's take a look at, by the way, this charge pump generates plus 10 volts, minus 10 volts, single 5 volt supply in an old board. And this new board, I'm not sure how much it is. That might be a good example of something to for you guys to actually measure. So I may actually add that into the lab. Have you actually measured the voltage using a logic analyzer? How many of you have actually used the logic analyzer? Or the oscilloscope will have you look at that too to see if you can see data coming across, and then also how much the voltage is. So here's what you'll typically do. Your computer system. Well, I got a minute. Ooh, almost. Is this the last one? Yep, that's the last slide. So, literally, all you have to do is you have to say, here, I'm going to write at this location right here, some memory location, I am going to put out here 8 bits of data. I'm just going to write a byte to a specific peripheral interface port. Then the hardware itself will add the parity, it'll add the start or stop bits, it'll add a start bit, and it'll send it out. Then when you receive, the machine will automatically bring everything in, strip off the parity bit, strip off the stop bits, and let you know if there's a parity error. And then also, depending on how you set it up, it may also let you know if it has a byte ready for you to read. So all you have to worry about with serial interfaces is setting up everything for the communications, and then you send a byte, you send a byte, you send a byte, you send a byte, or you receive a byte, receive a byte, receive a byte. And that will be discussion on Monday. Thank you very much.